recording. And Eric, if you're ready, I'm going to go ahead and switch screens to make you a presenter.
Okay. Okay, I just said show my screen. Can you see it?
I can, yes, perfectly.
Okay, great.
Okay, so whenever you're ready to begin.
All right, so let me click slideshow. Okay, good morning, everybody. My name is Eric Hansen. I'm a program manager in the SQL Server query processing team here at Microsoft, and I've been working for about the last 3 to 3.5 years on a new feature which is going to ship in SQL Server 2012 called the Column Store Index, and it's designed for decision support and data warehousing and to speed up data warehouse queries. So the topic of this talk is really kind of an advanced topic. It's about performance tuning with the Column Store Index. So in many cases, you won't need to do much performance tuning. So given the poll that was just taken, that about 2/3 of you are not very familiar with column store indexes at all, I'm going to take a slight detour and give some background information on column stores. So I may not go through all the information I had prepared, but I'll try to help give you background on column store indexes first, and then I'll talk about how you can tune your application to get the most out of column store indexes. So this is kind of a 300 to 400 level talk for developers and architects. That kind of person who's involved in a data warehouse probably would get the most out of it. By the way, if there's also a video of a talk that I gave in the middle of last year. It's from TechEd 2011 on the internet, which is more of an introductory talk. And at the end of this talk, I'll have a link that shows you how to find that talk. It's on our Channel 9 website here at Microsoft. So column store indexes are a new storage structure for holding data warehouse tables that instead of storing the data row by row, so we're in a typical storage structure that we've had in SQL Server in the past, rows are stored on pages. Every column of data for a specific row is typically stored on the same page. And so that when you're scanning a large fraction of a large data warehouse table, that has some inherent cost to it, because most data warehouse queries, when they touch what's called the fact table, the large data warehouse table that contains fine-grained business events, a typical fact table only has, it may have anywhere from 10 to a couple hundred columns, and it's not unusual to have 30 or 40 columns in a fact table. Most queries only touch 5 or 6 columns. So if you have to read every single column of the table in order to process a scan of the table, to process a query, then that introduces extra I/O cost. So column store indexes are basically, it's a kind of index that creates a second copy of your data structured in a different way, where every column is stored on a separate group of pages. So if you see this picture here, the red blocks, what that represents is a table that has 6 columns, and that's a little snippet of a query above that retrieves 2 of the columns. So you see that columns C2 and C3 are highlighted there. That indicates that the query processor only has to read those 2 columns from disk. So that right there produces a very large savings in I/O cost. You only have to read the columns that the query touches. In addition, the data in a column store index is highly compressed. So we have achieved compression ratios anywhere from like 4:1 to 15:1 compared to an uncompressed row store-based table. When I say row store-based table, I mean either a heap or a B tree. So by only pulling from disk the columns that you touch, and by compressing those columns very heavily, you can reduce the I/O necessary to run a query by a factor of 10 or even more. So that's the first thing that gives column store indexes their performance boost. But there's another even more important enhancement in SQL Server 2012 called batch mode query execution. And I'll say more about that later. But it's a new query execution mode which greatly reduces the amount of CPU time on a per row basis. So that's in addition, that's above and beyond the I/O savings that you get by just switching to a column-based data representation. Rachel, can everybody hear me okay?
We had one comment that you're a little faint, but I can hear you clearly, so if that person could please adjust their speakers, I think that would resolve the issue, because I can hear you perfectly fine.
Okay. I'll try to move a little closer to my microphone.
Thank you.
So column store indexes are, the sweet spot for column store indexes is data warehouses or data marts with a star schema. And you put the column store indexes on the fact tables. Usually your dimension tables don't need to have a column store index at all. You can leave them in row-based format. However, if you've got a really large dimension table, like maybe a monster customer dimension that has, say 100 million rows or more, then that may also be a good candidate for a column store index. And having column store indexes on your larger dimensions actually may simplify your database design process by eliminating the need to build lots of non-clustered B trees, because just scanning the data becomes so fast with a column store. So we can get 10 to 100 times query response time improvement for star join queries with grouping and aggregation, which is sort of the typical reporting query that you use in a data warehouse. And the value of this primarily is the benefit to end users. Because you can now get sub-second interactive response time to queries that used to take anywhere from 15 seconds to several minutes, or in some cases even tens of minutes, the users can get more value out of the data. They can explore the data much more quickly. They come up with an idea of some exploration they want to do on the data, formulate a query and run it, and bam, the answer comes back right away, instead of having to wait several minutes potentially to get the answer. And if you've ever used a data warehouse where your queries take several minutes, it can be tedious, right? You might lose your train of thought when you're running a query. When it gets done, like, what was I thinking when I first asked that query? So that interactive response time is really compelling. And that's going to lead to more business insight. So businesses that deploy this, that's the primary place they're going to get value out of this. In addition, there'll also be reduced costs. So cost savings come both from people costs and from hardware costs. So people costs will be reduced because it takes less effort to build your data warehouse in many cases when you're using column stores. Those of you who are sort of veteran decision support developers or architects, you'll be familiar with the idea that the way people used to get fast interactive response time for large data warehouses either was to use summary aggregates, like materialized views or indexed views or user-defined summary tables, where you for example, you might have raw data that shows the supermarket checkout transactions, but in order to get fast interactive response time for querying that data, it's very common to aggregate it. So you might aggregate sales by day by product, or sales by day by store, something like that. And that summary table or materialized view would be much, much smaller than the fact table, so you could query it interactively. And so it's an old trick to build these summaries and query the summaries instead of querying the raw, fine-grained fact data in order to get fast interactive response time. So this trick works, but it comes at a cost. One cost is that it requires relatively sophisticated developers to set it up. You have to decide what materialized views or summary tables you want to create, and you have to build them during ETL time. So that takes time during ETL and can slow down ETL, or database loading. Another way to get fast interactive response time is to use scale out. Use more than one node of hardware, and that has its own cost that it adds to hardware cost, because the scale out system just uses more hardware to solve the problem of being able to get fast interactive response time. And scale out has its merits. It's great when you need it, but if you can get fast interactive response time on a smaller hardware platform by having software that's more efficient, well, you want to do that to save money on hardware and electricity and floor space. So those are the benefits of column store index. All right, so a little background about the column store index. The way you create a column store index, well, the way you use it is create a table, load data into the table, and then you create what's called a non-clustered column store index normally you include all columns of the table in this column store index. So here's the syntax for creating a column store index. You can say create non-clustered column store index, the name on table name, and then a list of all the columns you want to be in that index. So column store index is different from an existing B-tree index in that it has no key. There's no notion of a key in a column store index. You just list out all the columns you want to be in the index, to include in the index, and it creates a second copy of the data in a second form on disk that's in that column store format that I showed you in the earlier diagram. So discussion objectives I had originally planned for this talk were to help you learn to make query performance go from good to really outstanding when you are using column store indexes, and help you understand the new batch mode of query execution and how crucial that is to getting speed ups in a column store index. And I'm still going to do that, but I would also add another objective, which is just understand what is a column store index and what scenarios are appropriate for column store indexes. Another thing I want to say is that there are a number of limitations, and this is a brand new feature, so there are some limitations, but when we planned the feature, we designed it in such a way that the large majority of typical decision support or data warehousing applications will be able to use this feature. So I'll talk about how to work around some of the limits in the feature in the initial release. So why should you pay attention to what I'm saying today? Well, here's a little cartoon to sort of give you a flavor of why you should pay attention. Users that have poorly tuned column store indexes are not going to see a huge benefit from column stores. You still might get a little bit of benefit, and when I say a little, I mean maybe your query performance will double or even triple, even if you don't do any tuning. It's not unusual. However, if if you make sure that you stay in the sweet spot of the column store implementation and tune your application if necessary to take advantage of it, you can get phenomenal, jaw-dropping query performance improvements. So, I've seen customers come into our lab and they'll bring their application and put it on one of our databases, and maybe the first hour or two they try it out and maybe things didn't speed up quite as much as they had anticipated. They're mildly impressed, but we'll go in there and work with them and make a few tweaks to some of their queries and some of their index structures, and bam, all of a sudden a query that, maybe a query used to run in 2 minutes and they got it down to 1 minute, and now we'll go in there and make some tweaks and get the query time down to a second. And at that point, it's a whole other user experience. It's thrilling. So if you're a data warehouse architect or developer who really wants to make the end user experience fantastic and a new type of experience with data warehouse data and data mart data, pay attention, because I'll teach you some tricks that can help you get that. So I'm going to now start to give a demonstration of column store index behavior. And I had an initial demonstration planned here which is going to be more oriented towards tuning, but I'm going to try to go back to an older demo. Hang on a second here. All right, right now I'm showing Management Studio, and I'm running a query in a database called Movlia 100M. Rachel, can you see the screen with the demo?
I can, yes.
Okay. So this is a data warehouse database, and if you go over here and you look in the tables list on the left, you'll see that we have a whole bunch of tables. The one that's most important for this demo is purchase. Purchase is a fact table. So you'll see right here it's got 101 million rows. The row count is 101 million. So it's a pretty big table, and this is running on my desktop PC, so this is not a huge machine. It's a 4-core machine with hyper-threading turned on. So it has 8 logical cores and has 12 gigs of RAM. So it's a pretty good PC, but it's not a huge machine. Now, here's the columns of the fact table. So it's a pretty typical fact table. You see it's got a date column. It's got several dimension key columns like user ID, user profile ID, offer ID, media ID, and some measure columns like price retail. So let's look at the indexes on this table. So you see that the indexes on the purchase table, there's 2 of them. There's CI_date. That's a clustered B-tree index on date. That's a typical type of index that you would put on a data warehouse fact table before the introduction of column stores. NCCI is a non-clustered column store index. So essentially that's a second copy of all the data in the B-tree, but it's stored in the column-based format, column by column, instead of row by row. So what I'm going to do here is I'm going to run this query. Let's see here. Hang on one second. I'll switch to a simpler query. So this query right here that I've highlighted, you can see that's a very simple star join style data warehouse query that's just got one fact and one dimension, and it's got group by and aggregation. So there's a query hint here called ignore non-clustered column store index, and what this is going to do is going to tell it don't use the column store indexes. So it'll run the same way it ran in SQL Server 2008, R2, and earlier. So I'm going to execute this. So this is a 101 million row fact table. So that query doesn't have any date range filters, so it had to scan the entire table, and it took 9 seconds and produced a little over 1,400 rows. So now I'm going to run it again, but I'm not going to use this hint. I'll comment out this hint. I'll just run this part. Bam, did you see that? I mean, the query came back instantaneously when I clicked. It's really incredible. I'm going to turn statistics time on, and we'll look at the summary statistics of time of execution. So I clicked again, it's just instantaneous. It did a full scan of the table with grouping and aggregation in split-second time on a desktop PC. It's 101 million rows. So see the total CPU time used was 731 milliseconds across all threads, and the elapsed time was 242 milliseconds, so just about a quarter of a second. So, if we saw 9 seconds versus a quarter of a second, so that's about a 36 times speed up. So that's kind of in the ballpark of this typical speed ups you can get if you've got a properly designed column store index and your queries are sort of in the sweet spot for a column store index. Rachel, could you see the demo okay?
Yeah, I could definitely see it. Is there any way to make the font a little bigger?
I can try. Let's see.
Okay. I mean, I could definitely see it clearly. It's just, the text is, I'm assuming 12-point font, so. Aaron is suggesting that you go to Tools and Option.
Tools, Options.
Aaron, you know where we go from there?
Fonts and Colors.
Probably. Oh, there we go. Perfect. So much better. Thank you very much, Eric.
Okay. Thank you. Is that Aaron Welker?
No.
Thank you, Aaron. All right. So, I'm going to go back and show a couple other more complicated queries. Like here is a more complicated query that has the purchase table, that's the fact table, a date dimension, and a media dimension, and it's got some filters on date and on media. So this is a database of information about movie ticket sales. So suppose I want to know horror, action, comedy ticket sales in this 2-month period. Let's try this. So that was just instantaneous. I'm going to show the query execution plan. Now this may be a little hard to see, but does Zoom It work through the GoToMeeting?
Yes, it does. Yeah, it absolutely worked. Yep.
Okay, great. All right, so if you look at this query plan, on the far lower right, it's a column store index scan. And it is, so that's scanning the column store and just pulling back only the columns that are referenced in the query. And you'll see that it's a cascading hash join. And that's a very typical data warehouse star join plan. So there's a new operator in there called batch hash table build. And I'll explain a little bit more what batch mode query execution is, but instead of one row of data at a time flowing through the query execution pipeline, like happened in SQL Server 2008 R2 and earlier, and what happens when you're not using column stores, instead of one row at a time flowing through query execution, the unit of query execution is now an object that contains about 1,000 rows. It's called a batch. And so it, by processing chunks of about 1,000 rows at a time, it amortizes the cost of query execution substantially, and it does query execution more efficiently and can save anywhere from like a factor of 7 to a factor of 40 on CPU consumption. So this is the kind of plan you want to see with column stores. You want to see a cascading sequence of hash joins, all of them having a batch hash table build, and a column store index scan of your fact table down in the lower right. That is sort of the plan that you hope to see most. Now, at some later stages in query execution, it's going to shift back to what's called row mode, and that's fine. But usually we try to summarize the data into a relatively small set of rows before switching back to row mode execution. So the heavy lifting is done in this new batch mode of query execution, and much faster than the final touches are done in row mode. Okay, so I've demonstrated for you that incredibly fast interactive response time you get with the new column store index and the new batch mode of query execution. And I showed you a 36 times speed up. So now let's go and talk a little bit more about how that happens. So again, the fundamentals of column store query performance are that each column is stored separately on disk on separate groups of pages, and the data is heavily compressed. So that reduces I/O tremendously. It might reduce the I/O to solve a query by a factor of 10 or more for a typical star join query with grouping and aggregation that you would see in a data warehouse or a data mart. And batch mode query execution is this new query execution mode that is much more efficient on a per row basis than the old query execution mode, which you get without column stores. There's also a feature called segment elimination, which reduces the amount of data flowing through the query execution system quite a bit in certain circumstances. And I'll talk more about that later, but just verbally to go through it now, a segment is a chunk of data from a table that has a column store index containing about 1 million rows. And there's some metadata for each column within a segment that stores the minimum and maximum value for that column. And so the storage engine, when it's starting to scan a segment, it peeks at that metadata that has the minimum and maximum value for each column. And if there's a filter on that column, it tries to check if any data between that minimum and maximum value might qualify against the filter condition. And if the answer is no, it skips the entire segment. So that segment skipping is very useful. And some of the competition, I think Oracle has something called a storage index, and Netezza has something called a zone map. So they all use similar concepts where it looks at the metadata for a larger chunk of data and attempts to skip the whole segment. So this is an effective way to reduce the cost of scanning the data. So the column store physical structure is based on this notion of a segment, as I described, there's about 1 million rows per segment. Each column within a segment is stored separately on disk, and the unit of movement between disk and memory is a column segment. So one of those sort of pale green blocks that represents one column worth of data from one of these 1 million row segments, that's the unit of movement between disk and memory and the unit of caching of data in memory. So if the query only touches the first 2 columns, it'll just read those first 2 pale green blocks of a segment, and it'll cache those in memory. Instead of caching pages, the column store now caches these special objects, which are column segments in memory. So one advantage of the column store index is that some people ask, is this an in-memory database technology? Well, the answer is not exactly, but it can take advantage of main memory very effectively. So because data is heavily compressed and only the data that you touch is pulled into memory, it takes a lot less memory to hold your entire working set in memory. So you can easily get essentially all the data that's necessary for your workload into memory, so you become effectively a main memory system. But the data doesn't have to fit in main memory, so if you've got a really huge database or an older, smaller hardware platform that doesn't have a lot of memory, then you don't need to have enough memory to hold all the data. So you kind of get the best of both worlds, a main memory level of performance, but the data is stored on disk, and it can be bigger than actually can fit in main memory. So the physical structure here again is, I talked about segments and the notion of a column segment. So each column segment is stored on disk as a blob or binary large object. There's also several different types of compression are used, but one of them is dictionary compression. So if there's a small set of discrete values for a column, one way we can represent that is create a dictionary that holds those discrete values and use like an integer lookup key to represent each discrete data value, and that's used to look up into a dictionary. So there can be multiple dictionaries for each physical table partition. So those of you who are familiar with table range partitioning in SQL Server, range partitioning works just fine with column stores. It's actually recommended as a way to load data. So one limitation in the initial release of column stores, probably the biggest limitation, is that column store indexes are read-only. Once you create a column store index, you can't insert, update, delete data in a table. So in a data warehouse environment, this isn't as big a limitation as you might think, because most data warehouses have a nightly load scenario where you're not really updating data during the day. You just have a nightly extract, transform, load process where you take new data and append it to existing data and rarely modify existing data. So one way to do the load would be to drop the column store index, just do your load process just like you did before, and then rebuild the column store index. That may be perfectly workable. It takes about 1.5 times as long to build a column store index as it takes to build a B tree on the same data. So it's a little bit more expensive than the regular index build, but it's not an order of magnitude more, it's just a little bit more. So that's one of the biggest limitations. But you can work around it either with that drop, load, and rebuild strategy that I described, or you can use table partitioning. So you could switch a table, you can create a staging table every night or every time you want to do a load, put a column store index on it, and then switch it in as a new partition into your data warehouse fact table. So we polled a lot of customers before we decided to ship this and found out that virtually all of them can accommodate this limitation of not having true update DML support. Or that's insert, update, delete, and merge. Rest assured, we're working on adding update DML support in a future release, but I can't give you any specific timeline right now. There's also a catalog that holds the metadata, descriptive data about each segment and each column segment. So for each column segment, we store the minimum and maximum values in that column. So I mentioned batch versus row mode, and you can sort of, the difference between batch and row mode is really stark, that the overhead for processing data in a batch mode is much, much less. So batch mode is sort of like a semi-truck full of boxes zooming down the freeway, and row mode comparatively is like one person wheeling some boxes on a little cart. So here's a little deeper dive into what batch mode processing is all about. So a batch is an object. Again, it's the unit of execution now. It's the unit that flows through the query execution plan. Instead of a row at a time, we use batch at a time. So batch mode processing stores about 1,000 rows in an object called a batch, and each column of data within that batch is stored as a vector internally, and just like an array of values. And those values, doing operations like filtering and so forth, the overhead to do that is quite a bit less because code just burns through that vector in a very tight loop, and it's really quick. And so there's, for filters, when you filter something out, you just mark it as no longer valid. Doing joins requires less copying of data in memory. So overall, we can reduce CPU time by anywhere from like a factor of 7 to a factor of 40 to do a typical star join with grouping and aggregation. So that's where most of the query speed up comes from once you've got all your data in memory when you're using column store indexes. Rachel, how are we doing? You still here?
Yep, we are good to go. And we've got a ton of questions for whenever you have a moment.
Okay.
And we can do it at the end of your presentation if you'd like.
Okay. So the number one takeaway from this talk about tuning column store indexes is make sure that most of the work of the query happens in this batch mode of query execution. So I've shifted gears in this talk to talk more about the background of column stores. Now I'm going to talk about some more advanced concepts about tuning. But I'll get to that soon. One thing that I mentioned is this segment elimination idea. And so again, a segment is a 1 million row chunk of data. We also use the term row group to mean segment. So row group and segment are sometimes used as synonyms. From time to time, we also talk about segments as column segments, so a single segment of a single column. So our terminology is not 100% consistent, but when we say row group, that means a 1 million row chunk of a table, including all columns of the table. So for each column in a segment, we keep the minimum and maximum values, and scans can skip segments based on this. So look at that little query on the right. It says it's selecting date and and doing a count group by date from the fact table purchase with a simple filter on date that just says date is greater than or equal to that specific date, February 1st, 2012. So if you look at the column segment minimum and maximum value in the little table on the left, look at the min and max, and you can compare that to that constant that's in the query. We see that the first row, that's January. All the data is somewhere in January. It's not February, so obviously that row is not going to qualify. So the other two rows do contain some data that overlaps with that condition, date greater than or equal to February 1st, 2012. So you can see that that entire segment can be skipped. So that would not even be read from disk. That's segment elimination. So the main thing you want to take away from this talk is you want your queries to run in batch mode as much as possible. but you also want to make sure that you're getting segment elimination. So at this point, I want to take, I'll take questions for like 3 minutes. And Rachel, why don't you pick the questions?
All right.
And
Great.
then I'll go to the end, and then I'll take some more questions.
Okay. So here's the first question. Does a segment equal 1 million rows?
Yes.
Okay. That was easy enough. Is segment elimination supported for all data types supported by column store?
No, it's not supported for string filters. So that's something we plan to add in the future, but we don't have a timeline for that yet. So it works best for integers and dates, floating point numbers, numerics. It doesn't work so well for strings.
Okay. What version of SQL is column stored index function available?
It's going to be in SQL Server 2012 in the Enterprise Edition.
All right. Jason would like to know, can you alter the batch size?
No.
Okay. And let's see, with differences in time, is caching considered since this is the second time the query was run?
I'm not sure I understand the question.
I'm not sure either.
Let me go to another question.
Okay. If you want to clarify, please do clarify in the question box and we'll try to get you an answer. What is the cost time in building the column store index?
The cost and time to build a column store index?
Right.
It takes about 1.5 or 2 times as long as it takes to build a B tree on the same amount of data. So for example, on my desktop PC, which is 4 cores, it takes about 6 minutes to build a column store index on 101 million rows.
Okay. John would like to know, what if you clear your buffers between 2 different queries? What would happen?
So if you do drop clean buffers, it clears the column store cache and the page cache, so it will read the data from disk again. But normally it buffers those column segments in memory in a new kind of buffer pool that's different from the page buffer pool.
Okay. Do you want me to go on, or?
Yeah, these are good questions, so keep them coming for a couple more minutes.
Okay. Murali is asking, his BI system gets data for the production box by using transactional replication, so he can't utilize column store index?
You can't have a column store index on the target of replication.
Okay.
So you might be able to work around it by using transactional replication into some tables that don't have column store index and then copying the data over and using partition switching to switch data in, but you'd have to use some significant workaround, so it wouldn't normally just work.
Okay. The next question is, let's see, does this replace cubes?
Does it replace cubes? So that's a really good question. And the answer is, in general, no. But because you can get really fast interactive response time against the source data, if your queries are in the sweet spot for this technology, in some instances you may be able to do just straight reporting on the decision support database itself without creating a cube. If you want the best sort of development experience for reporting, like Crescent and so forth. Crescent does work in sort of a relational OLAP or ROLAP mode on top of column stores, but it works quite a bit better on top of the in-memory BI column store that they have in analysis services. So, for the slickest experience, I think using cubes is still going to be better in terms of the slickest end user experience. But if you want to avoid the need for a separate hardware platform and for copying the data, and you're willing to write your queries by hand and use more of a traditional reporting system, like the older reporting services features or third-party reporting tools or Excel or whatever, it may be quite adequate to just query directly off column store indexes.
Okay. Stuart would like to know about space. When a column store is created on a 5 gigabyte table, does that mean another 5 gigabytes for an index?
So no, like if the 5 gigabyte table is an uncompressed heap, say, and it's a typical data warehouse fact table, your column store index is probably only going to take like 700 megabytes. It'll be a lot smaller. It'll be about 1/7 the size of the raw data in uncompressed row-based format.
Okay. Mike would like to know, is the data inside each segment sorted?
The data inside each segment is not sorted. It's more like a heap than an index. It doesn't have any order.
Okay.
Although it's a good idea to load your data in a specific order to try to get better segment elimination. And when you build the index, it tries as much as possible to preserve the index order of the clustered B tree that it was loaded from.
Mm-hmm.
And also if you're using partitioning, then that creates some sort of partial order of the data, and that segment elimination can take advantage of that.
Okay. Paul would like to know, would you use an index on a large OLTP table with millions of rows?
No, you would not use this in OLTP because you can't update the data.
Okay, that makes sense.
Now, I have heard from some people that are OLTP architects that they'll probably figure out a way to use this in an OLTP application for, they might have a separate set of tables that are used for like for something like an operational data store that's embedded in the same database as the OLTP data, to go back and like maybe query historical data to present graphs or something like that. So you might see some hybrid applications that have some tables that have column stores that have historical data that maybe only is updated at night, but it might be queried by the OLTP application because they know they can get sub-second response time. So that, I've heard people contemplate that. That may happen.
Okay.
You keep going. These are good questions.
Oh, great.
One or two. Take 2 more questions.
Okay. Will column store be supported in SQL Azure?
I anticipate eventually it will be supported in SQL Azure, but it won't be supported probably this year.
Okay. All right. Can you propose a few possible solutions to update data using column store indexes?
Yes, the 2 main, well, there's 3 main ways to update data. One is drop the index, do your updates, and rebuild. The second one is to use table partitioning. So you can create a new partition and then switch data into a column store index table. Partitioning works with column store indexes. A column store index has to be partition aligned with the underlying heap or B tree. And a third way is you can do some tricks to, you can create 2 tables, one with a column store index and another table with the same schema that doesn't have a column store index. And basically you can insert data into the regular table and then query both of them and combine the results. And so that, if you're willing to do some special extra coding in your queries, you may be able to do that and get some sort of trickle load, but still get the performance benefits of column store. And I have an example of that. I'm not sure I'll have a chance to get to it. But. Okay, that's it for questions. So some do's and don'ts with column store to get good performance. Use the star schema. Put column store indexes only on the larger tables, that is the fact tables and maybe your monster dimensions. Include every single column of the table in the column store index. It's a second copy of the data. It is not in the columns you use when you create the column store index. They're not a key. It's like an included column. It just includes every column. You want to include every column in the index if you can. Now, there may be some exceptions. There are some limitations on data types with column stores, so you may need to either change the data type to some columns, or if you don't really need them that much, you might just leave them out of the index. Use integer surrogate keys to join with your dimensions. So don't try to create a surrogate key that's like a character string. That doesn't tend to work very well. Use integers. And structure your queries as star joins with grouping and aggregation as much as possible, because then you'll get those batch mode query execution plans more reliably and get the best performance. Don't join on string columns, as I mentioned, if you can avoid it. Try not to filter on string columns of a fact table that has in the column. If you have a fact table that has strings in it, the filters work okay, but they don't get pushed down into scans of the fact table. So you may want to consider normalizing the strings out into separate dimension tables. Try to avoid joining pairs of very large tables. That's like if you have a normalized schema like orders and line items, two very huge tables, it's not going to work as well as if you try to join those together into a single line item table that's extended with some of the tables of the order, some of the columns of the order. So, use a star schema. Try not to use a normalized schema. Certain types of operations are like not in and union all and outer join tend to reduce the benefit of batch processing. So you want to avoid those if possible. I'm going to show a little demo of a workaround you can do with outer join to sort of get good performance. I'm going to go back to the demo here. So you'll see this query, which I already ran, uses an inner join, and it runs with almost instantaneous response time. If I just change that query a little bit and change it to a left outer join instead of an inner join, see the difference? I'm going to run this one. Boy, it takes a lot longer. Still running. It takes about 5 seconds. So let's look at the query plan for this one. So if I zoom in, you'll see that, yes, on the lower right, it is scanning the column store index, so we're getting some I/O savings there, but it's not using the batch mode of query execution. So the hash joins are not batch mode hash joins. It's this harder to see here, but if I click on that one, it says the estimated execution mode is row. So I want the execution mode to be batch. So if I look at this one, if I do the show plan, the show plan for this one has a batch hash table build, and if you look at that, the estimated execution mode says batch. I know that may be a little hard to see, but you want to look at your show plans and make sure that most of the work of the query is done in this batch execution mode rather than the row-based execution mode. That's sort of the #1 takeaway of this talk about tuning. Okay. So how can I work around this problem? So what if I really need an outer join? If I need outer join behavior in my query, but I want the query to run fast, what can I do? So here is a workaround. This is outer join workaround. So that workaround, basically, if you look at this subquery right here, which is in a common table expression, it uses a regular join, and it has a group by clause, so it's going to summarize the large volume of data in that purchase table down to a very small volume, just probably a few thousand rows. And then I'm going to use an outer join down below to extend the results so that I have the media rows for which there are no facts that participate in the query. So this workaround here, I've rewritten the query to give the same meaning, but if I run it, you see it runs in instantaneous time. I mean, it It's like a quarter of a second or less, third of a second. So workarounds like this, the way they function is by doing most of the work in batch mode. So let me show this. All right, so you'll see on the lower right, it's a column store index scan. The upper right, it's a batch hash table build. So that is joining the column store index to that media table. And the hash match there at the top and the partial aggregate, that's going to winnow down the total number of rows that are participating in the query execution to a pretty small number, like a few thousand. And then after this, after that part, if you look on the far right, upper right, it says hash match, partial aggregate. Let me wait for your screens to redraw. Okay, hash match, partial aggregate on the upper right. Everything after that, you see the lines, the arrows are a little skinnier, so fewer rows are flowing through query execution. At this point, it switches back to row mode. But that's okay because not that much data is being processed in row mode. So if you can get the bulk of the work of your query to run in the batch mode of query execution, then the remaining work can run in row mode. And it doesn't take that long because it's not really operating on very much data. So in a nutshell, that's the number one thing you should take away from this talk. And I don't have time. I had a whole bunch of extra examples about other types of possible performance problems that you can run into where you're not getting batch mode as effectively as you might want. And I have written a bunch of information on the TechNet wiki. I'm going to show you I'm going to jump ahead to this related content slide. So there's three things you should be aware of. There's the column store tuning guide. So that discusses that workaround for outer join, as well as a bunch of other related information about how to make your column store index-based applications run fast. And the column store FAQ is a frequently asked questions document that answers frequently asked questions about the column store. And then there's an introductory column store talk video that's from TechEd 2011 that covers a lot of the things I talked about today. So I actually changed the format of today's talk to mainly focus on the basics of column stores, with a little less on tuning, just based on the audience, because at the poll at the beginning, about 2/3 of the audience wasn't very familiar with column stores. But if you want to learn more about tuning column stores, take a look at the column store tuning guide. So if you just do a Bing search for a column store tuning guide, it should be your first hit. And there's a lot of material there with examples of performance problems that you can run into with column stores and how to work around them. So if you're a column store, if you're going to be a column store developer or data warehouse architect, definitely go take a look at that. At this point, I'll take some questions.
Okay, great. We have a few more. Joseph would like to know, isn't the column store index essentially a covering index without a storing key?
So the question was, so I guess everybody heard the question, is it like a covering index without a key? And the answer is yes. But it's a little different in that it's kind of like a universal covering index, in that because people used to use covering indexes to reduce I/O for queries that only needed a subset of the columns. Mm-hmm. But now you only pull from this the columns that you need, no matter what subset of the columns you're touching. And so it's kind of like a universal covering index. It just reduces I/O, regardless of the subset of columns you touch.
Okay. Sheila would like to know if she can use a column store index with one specific table when we have an OLTP environment, and when that would be useful.
I think you could use a column store index on one table or a few tables in an OLTP environment. Maybe you might want to say have summary of you might have historical data from the previous day and days before that in sort of what I'd call an operational data store, pre-prepared in column store format, so that you could do some light reporting inside the OLTP application that did group by and aggregate type queries to maybe plot graphs for people if they wanted to have the ability to do that.
Okay. Do you foresee improving on the limitation of only having a single non-clustered column store index per table, and that no clustered column store indexes are available yet?
Yeah, so we anticipate in the future enhancing column stores so it can be the clustered column store index and be the master copy of the data.
Mm-hmm.
So you wouldn't need the row-based copy of the data at all, and that would give you a lot of storage savings. Mm-hmm. Because column stores are very compressed. So that's on our roadmap, but I can't announce any timelines.
Okay. And another question from Mike. Is the compression used in a column store index similar to page compression features?
The compression techniques used in column store are different than page compression. I mean, there's some similar concepts used, like dictionary compression, but there's a page-level dictionary and page compression, and column stores have off-page dictionaries, and it's quite a bit different. But compression technology, as it all tries to take advantage of redundancy in the data and eliminate the redundancy. So in that respect, they're similar, but the implementations are quite different.
Okay. And we only have 2 more questions. It is the second to last one is, would it be overkill to have 2 similar tables in the database, having one with the column store index and one without?
Usually, yes. Usually you want to have a one with a column store index, and underneath it there's a B tree or a heap. So it's possible that the query optimizer could decide to use the B tree for certain queries. Mm-hmm. On the other hand, I can see applications where you might want to have 2 copies of the data, one with a column store and one without, and you could update the copy without the column store, and then maybe every 15 minutes you could rebuild the column store on that copy, drop the column store on the other copy, and switch your queries from one to the other, and then catch up the other copy of the data which had been read-only for a while to the current state. That's a way to work around the inability to update. Okay. So I think that there could be situations where you do it.
All right, and our last question is the index only compressed or encrypted as well?
No, it's not encrypted. So anything any encryption features that would encrypt all data in the database, that would work because it's just database data. It's within the database, just like any other data. It works with backup and restore and so forth. And yeah, that's about all I can say on that one.
Okay, great. Well, thank you so much, Eric. That is all the questions we had, and it was a wonderful presentation, and we very much appreciate it.
All right, thank you all. Appreciate your attendance. Thanks, everybody, and go out and try it and let us know how it works.
All right, everyone have a great weekend.